Okay, so yesterday we looked at um, so what did we cover yesterday? Yesterday we looked at elementary things such as properties, yeah, the properties of fluids and all those things. So let us continue on that dimensions and units. So some of the things that we covered yesterday, such as pressure, temperature, density, viscosity. Okay, so the units of pressure, Pascal, okay, essentially which is Newton per meter square. So units of temperature, Kelvin, degree Celsius, units of density, kg per meter cube, units of viscosity. How do you find the units of viscosity? So let us look at the definition of viscosity. So the definition of viscosity was shear stress is equal to mu times del u del y. So tau units is, the units of tau is Pascal, while the unit of del u del y, so u is meter per second, while the unit of y is meter. So meter gets cancelled, so it is effectively 1 upon second. So Pascal times, so Pascal equal to viscosity units multiplied by 1 upon second. So the unit of viscosity is going to be Pascal second. Okay, so it is Pascal second. So these units are called as SI units. SI stands for System International. It's a French organization which sort of organized all the units, because initially there were a bunch of imperial units. So can you give me some examples of some imperial units that you know? Pound. Pound. So for mass, SI unit is kg, but the imperial unit is pound. So LB. So inch. Good. So in SI unit, length is meter, but they have inch, foot, all those weird things, yard, mile. Okay. So we're not gonna discuss too much about all these weird imperial units. And in my second video, I have discussed about the hazards of using heterogeneous units and all these things. And I've put in two prominent examples where the units and their hodgepodge led to a very catastrophic incident. So the first incident that I discussed in the video is called as the Gimli glider, and the second incident was the Mars orbiter. Of course, there are similar, I mean, not similar, there are many such incidences, but these two have gained prominence in science and engineering because of the monetary nature of the work. Okay. So anyway, you can have a look at the video. Okay. So in that video, I discuss more about imperial units, but in this lecture, rather in not just this lecture, in this entire course, will not at all deal with imperial units. We'll only deal with SI units. So unit is something which is like a quantification of how much of a quantity is there. So like 1 kg, meaning one amount of kilogram is there. But what is a dimension? So the dimension is sort of the basis of that particular unit. or not of that unit but of that quantity. So it is the basis of the quantity. So what do we mean by basis? It is something which constructs the dimension of that entity. So consider length. So length is having a dimension of m to the power 0, l to the power 1, t to the power 0 and theta to the power 0. So theta is temperature, so m is mass, l is length, t is time, theta is temperature. Apart from this, you can have units such as amperes and so on. But since we don't deal with all that, let's proceed. So essentially length is a fundamental unit and hence it appears in this list. So all these are the fundamental building blocks of all the quantities that we will see. What about mass? It will simply be m to the power 1, l to the power 0, t to the power 0, theta to the power 0. So what about velocity? Who can tell me? Velocity?
LT minus 1. M to the power 0, L to the 1, T to the L minus 1.
Good. So we see that velocity in its fundamental form is comprised of the basis of length and time. It is comprised of the basis which contains length and time. So the density, what do you think it will be for density?
M1 L0 T M1 L minus V T0 theta 0.
So great. So I mean this is something which you might have done in class 11 or something, right? So just for completeness, this is what a dimension means. So now tell me the dimensions of force.
M1 L1 T minus 2. MLT for
So again, what will be length?
L1 L1 minus it is
What about pressure?
M1 L minus 1 T minus.
Excellent. So pressure is just force upon area. So area has a dimension of m0 L2 t to the power 0 theta to the power 0. So you just divide the dimensions and you get the dimensions of pressure. What about viscosity? So we just saw that viscosity has Pascal second. The unit of viscosity is Pascal second. So it is nothing but pressure multiplied by time, right? Because the unit was nothing but Pascal second. Now dimensions are one thing. Now you may think that okay, dimensions are fine. I mean it. What do you think is the use of knowing the dimension? What do you think is the use? Anyone? What does it strike you? Why should I know what the dimension is?
Sir, we can tell that foot and meter are used to express the same quantity because they are the same dimension.
Okay, that's a very good answer. The answer that I received is dimensions are independent of units, right? So dimensions being independent of units means I can tell that this entity should have the certain dimension and then you can think about what unit you want. You can very well define some new unit. Okay. Okay, what else?
When we do computations, knowing the dimensions help us to check for dimensional accuracy, dimensional correctness. So that we don't add quantities that don't make sense together.
Okay, so what you said is, uh, I mean, it's correct, but the way you phrased it is slightly incorrect. So whatever you said is dimensional accuracy. So that is something else. Dimensional accuracy refers to the preciseness of an object. So if I say that this has to be 1 millimeter, so the dimensional accuracy will say plus minus 0.1 micrometer. That is the dimensional accuracy. But okay, what he wanted to say, if I got his essence correctly, is I don't want to end up adding 1 second with 1 meter. Okay, I don't want to end up adding heterogeneous quantities. So dimensions help us in maintaining homogeneity, meaning that in a given equation or in a given expression, all the terms must have same dimensions.
Sir, dimensions can help us determine what kind of quantity is a constant of proportionality, like coefficient of viscosity.
Right, right. I'll get to that. So before getting to that, let us quickly see the Bernoulli equation. So what is Bernoulli equation? P plus half rho u square plus rho g z. I mean the Bernoulli equation that you have studied in class whatever. Studied this, right?
Yes.
Yes, sir.
So the dimension of this particular term is that of pressure. So what was it? M L T to the power, what was it? Minus 2. So now if you quickly check that the dimensions of rho u square, they should be exactly equal to the dimension of this fellow. So let us see. Rho is what? M L to the power minus 3 T to the power 0. And what is the dimension of u? It is M0 L1 T to the power minus 1. So what is now the dimension of u square? It is M L to the power 2 T to the power minus 2. So this is u square, this is rho. So what is the dimension of rho u square? M L to the power minus 1 T to the power minus 2. So there you go. Rho u square has the same dimension as pressure. Don't worry about this constant, because a constant by definition is dimensionless, right? Now in your notebook, I mean, first of all, are you sitting with a notebook at all?
Yes.
I mean, that would be very odd to just sit blankly staring at a screen. So I request you to take 2 minutes of your time and quickly do this computation. Do find out the dimension of rho gz. See, I want this entire thing to be as interactive as possible. Okay, please do that. And after doing, someone will uh, volunteer to tell us the entire working of rho gz.
Yes, sir.
Yes, sir, we are done.
Let other people also do. Let me randomly choose someone. That way, I mean, slightly better. Let's see. Jaswant Gopa, is he there in the class? Jaswant? Okay, so he's not there. I mean, he's there in the class, but he's not there physically. Okay, no problem. What about Jatin Saini? Jatin?
Yes, yes, sir.
So Jatin, can you tell us the calculation?
Yes, sir. The dimensional formula of density rho is m1 m to the power 1 l to the power minus 3 and t to the power 0.
Okay.
And then the dimensional formula of acceleration g is m to the power 0, l to the power 1 and t to the power minus 2.
Okay.
And for z it will be m0 l1 t0.
Okay. So when you multiply,
So when we will multiply, it will come m to the power 1, l to the power minus 1, and t to the power minus 2.
very good. So that has the same dimension as that of pressure, right?
Yes, yes,
Okay,
sir.
good, good. So at least I am assured that there are people who are attentive. Very good. I'm very happy. So let's continue. Let's continue. So apart from having these kinds of checks that they're independent of units, okay, they have must have the same dimension. So there was someone who suggested that it will help us find out the constant, right? But actually, that is like a corollary of something greater. Whatever he just said, that is actually a corollary of something much greater, and that falls in the extremely useful topic of dimensional analysis. And I can assure you that this topic is not just relevant for fluid mechanics, but it is very, very relevant for any kind of physics that you do. And you will find this topic very useful for absolutely anything that you will encounter. So let us consider an experiment. Okay, let us consider an experiment where you have a, again, before even going to that, before even going to that, let us consider the example of a simple pendulum. Okay, so what are the various parameters in the problem? So one may think that, okay, I have the mass of the bob. What are the other parameters? The length of the string. What else? Gravity. Let me write down the different parameters. Length of string, then the mass of bob, gravity, and of course the important parameter that I want to find out is the time of oscillation, right? I want to find out the time of oscillation. So let us write down the dimensions of all these quantities. Length of string, m to the power 0, l to the power 1, t to the power 0. Mass of bob, m to the power 1, l to the power 0, t to the power 0. Gravity m, l to the power 1, t to the power minus 2. Time of oscillation m to the power 0, l to the power 0, t to the power 1. Okay, so right now we have this, and can you recall and tell me what the solution will be? Who can tell me what the time of oscillation is?
That's pi under root L by.
Excellent.
Pi under root L by.
So time of oscillation is equal to 2 pi square root of L upon G. Now, as per our assertion that all terms in an expression must have same dimension. So let us check it. So what are the dimensions of t? M to the power 0, L to the power 0, t to the power 1. What are the dimensions of L upon G? So L has dimension of Rather, let us directly write it. So it is square root of m to the power 0 L to the power 1 t to the power 0 upon m to the power 0 L to the power minus 1 L to the power 1 t to the power minus 2. Essentially, it is m to the power 0 L to the power 0 t to the power 2, which is nothing but m to the power 0 L to the power 0 t to the power 1. So obviously, square root of L upon G has the dimension of time. But you know what? We could have actually arrived at something which resembles this even without solving for anything. So to obtain this, you need to do a lot of things, simple harmonic oscillator, blah blah blah. But with a little bit of physical insight, we could have actually obtained this expression. Now look, nature is actually independent of our mathematics. Nature is has nothing to do with our rules. So our rules meaning mathematics, units, even physics. It has nothing to do with our understanding of all these things. So our abstraction is only to understand the working of nature. Our abstraction has, I mean, it has now gone to a very weird state where we want to do things which we don't understand. But actually, if you look at scientists back in the day, for them, understanding nature was the key thing. And that is why everything used to be called as natural sciences. So now nature does not depend on all this. So if nature does not depend on units, we must have some description of the physical phenomenon which is devoid of any units. Okay, there must be some description that must exist which should be devoid of units. That means that we must have some expression to express the physical process which should have no dimension. It should have no dimension. Let us go back to our example and let me copy paste this, copy paste all of this. Now our assertion is we should be independent of the dimension, but right now I'm seeing a bunch of dimensions. So we must construct a term or multiple terms. We should be able to construct multiple terms which should have no dimensions. If we can construct multiple terms which have no dimensions, then we can say that the physics of this problem will depend in some functional form on the multiple terms that we derive which will have no dimension. So let us see how we can construct a term. So right now let us do it by inspection. So let us consider t divided by square root of L upon G. So t divided by square root of L upon G has m to the power 0 L to the power t to the power 0. So I have made use of this term and this term to obtain a dimensionless quantity of t upon square root of L upon G. What about the mass? Can I construct? So the question is, can I construct a dimensionless term which contains mass but is dimensionless? Okay. So can you construct, think about it, can you construct a term which contains mass but is dimensionless.
So we'll probably need some fixed mass that we could, cancel these units with.
Very good. So that's a very good observation that we need another mass somehow to cancel the mass. But there is no other mass in the problem. If there is no other mass in the problem, right, there is no combination of mass, gravity, length of string and time of oscillation. So I cannot find any expression of the form m to the power a, l to the power b, g to the power c, t to the power d. There exists no combination of a, b, c, d for which I can render this expression dimensionless, because m to the power 1 cannot go away by raising length, gravity and time to any power, because in all of those expressions mass always has a power of 0. So I cannot have a dimensionless term which includes mass. Hence, mass must not come into the picture while determining the physics of this particular problem. And this is exactly what you see, because the time of oscillation nowhere has the expression for mass. Okay, so the only term we could construct is T upon square root of L upon G, right? And that is why if we have only one term, that one term should be equal to a constant. Now this much you can understand from pure dimensions, and what the value of the constant will be you have to determine through experiments or some analysis. Okay, is it clear? Now let us formalize the whole thing. Let us try to formalize the whole thing. In order to formalize the whole thing, we must understand certain things. The first thing is basis. So if I have n number of terms, each of which has certain dimension. So this is the first term t1, t2, t3, tn, and each of them has a mlt dimension. So suppose this is 0, 1, 0. So suppose term 1 is length. Term 2, suppose the unit, suppose the term 2 is velocity. So velocity will be m to the power 0, l to the power 1, t to the power minus 1. Third term is mass. Let's say I have pressure. So what was the unit of pressure? Who can tell? Was this it?
L minus 1.
L minus 1.
L minus 1, T minus 2.
2.
T will minus 1, T minus 2.
Yes, sir.
And so on. So let us take some more few terms. So what was the dimension of viscosity? 1 minus 1 minus 1. So now given these 5 terms, how many dimensionless terms can I make? The question is, how many dimensionless terms can I make? So if I were to have, so that is the general question. Let me pose a even simpler question. Let me say I have two lengths, one length is L1, one length is L2. So the dimension is this, right? So how many dimensionless terms can you make from this? Only one dimensional term. And that dimensionless entity will be L1 upon L2 or L2 upon L1, doesn't matter. Now suppose I take 3 lengths. Now how many dimensionless terms do we have?
0.
No, we will have 2 dimensionless terms. L2 upon L1, I mean keeping one term as the basis, L3 upon L1. So if we have only one basis term, okay, the number of terms here are 3 and the number of basis terms are 1. So if this is the case, the number of dimensionless terms will be n minus b, which is equal to 3 minus 1 equal to 2.
What do you mean by basis term?
I'll explain. So the basis with which we can construct the other terms. Okay, let me write it as this. So suppose I have length and area. So length has dimensions this, area has dimensions this. So
0, sir.
and say suppose volume. No, not 0.
0.
Oh, sorry. Easy.
0.
Okay. So how many dimensionless terms can you make? You can make 2 dimensionless terms. So area upon L square and volume upon L cube. So I can represent area
So
and
volume upon area into length.
no. So we are trying to keep only one basis. See volume. See, because I could represent area in terms of length, there is no point in me sort of representing volume as area into length. You get my point? Because I have already expressed area in terms of length. Okay. So that is only 2 dimensionless terms we can form. Of course, you can always write volume upon area into length, but area itself is length square. So then it will effectively become L cube. So it is one and the same. Alright.
So we can't take higher powers of area or volume.
No, so of course I can write dimensionless terms if I choose area as the basis. So these are the dimensionless terms where length is the basis. I can equivalently write the 2 dimensionless terms keeping area as the basis. So L upon square root of area and volume upon area raised to 3 by 2. So these are also equivalently valid. So it all depends on what kind of basis you take. So essentially we want to find out, if I have these many terms, what kind of basis can I form? So if you consider each of these things as a vector, if you consider these dimensions as vectors, essentially you want to find out what is the basis vector of your problem. So now let us quickly look at the concept of a basis vector. So in 2 dimensions, if I have a vector say 3i plus 2j, the basis vector for this is I and j. So I take the basis I and multiply it by 3 and I add it with the basis j and multiply it by 2. With the help of this basis vector, I can construct any 2-dimensional basis vector. Okay. But is I and j the only basis? The answer is no. In fact, any 2 vectors in the plane which are non-collinear can also form the basis of my vectors. So suppose this is my basis 1 vector, basis 2 vector. I can represent any other vector as a linear combination of these two also. Okay. So these are the components of the random vector on the basis vectors. So if I choose this vector and this vector as the two basis vectors, I can multiply or add these two vectors. I cannot get anything else apart from some vector which lies on this same line. That is why these b1 and b2 are not the basis vectors in order for me to obtain any other vector. So for obtaining the basis, I must find out three linearly independent terms with the help of which, not three independent terms, I must find out linearly independent terms which will help me represent other terms as a linear combination of the others. So it is best done through an example. So have you come across the term rank of a matrix?
Yes, sir. So we actually had a linear algebra course last semester.
In first year?
Yes.
Okay, good. So that will make things easy. So now suppose I have a bunch of vectors 1 1 0 2 0 1, not 2 0 1, 2 0 0 1 0 1 3 2 2. So who can tell me what the rank of this matrix is?
3.
Please.
So how do you find out the rank of a
Three, sir.
matrix?
Non-zero rows. Number of non-zero.
Yes, sir, non-zeros.
Linearly independent columns or
Yeah, exactly. So I mean both both are correct. So non-zero rows, non-zero
Dimension of row is 10.
non-zero columns, but actually the fundamental definition is something else. It is the dimension or the size of the smallest submatrix,
which is not singular.
which is not zero, which is non-zero. So obviously this
So non-zero as in its
determinant, the determinant has to be non-zero.
determinant is not zero. Yes.
So who? So consider this submatrix, and obviously this determinant is not zero. Okay. So it means that the rank of this above matrix is 3, and because these 3 columns are yielding a non-zero determinant, these 3 columns, each of these column vectors can be chosen as a basis vector. So if they are the basis vectors, if these 3 are the basis vectors, I should be then able to construct this fourth vector as a linear combination of these 3 vectors. Do you agree?
Yes, sir.
Yes, sir.
So that is what the whole idea about a rank is. So I should be able to construct 3 2 2 as a linear combination of 1 1 0 2 0 0 1 0 1. So who can tell me what the linear combination is going to be? Please.
2 minus 1, 2.
Oh, very good. So the linear combination is, so tell me, twice of
Twice of 1, 1, 0
1 1 0 plus
minus 1.
minus 1 times
So minus half. Minus half.
minus half times
2, 0, 0.
2 0 0 plus
Twice
twice of.
1, 0, 1.
So I allow you to check it. I allow all the audience to check it. So, but anyway, so now we know that given a matrix like this, if I am able to find out a non-zero submatrix, right? Not a non-zero submatrix, a determinant which is non-zero, then I know that those vectors, those column vectors will be the basis for all the other terms in the matrix, in the larger matrix. So in this case, these three column vectors were the basis for the fourth vector. So let us go back to our example. In fact, let me copy this so that so the first thing that we do is we represent the MLT in terms of a matrix. So length, velocity, mass, pressure, viscosity, MLT. So everything, let us write it like this: 0, 1, 0, 0, 1, minus 1, 1, 0, 0, 1, minus 1, minus 2, 1, minus 1, 1. So in this particular case, what is the rank of this matrix? What is the rank of this matrix? So which are the three column vectors which you have used to find out the rank?
L, V, M.
So let us choose L, V and M. So the column vectors are 0, 1, 0, 0, 1, minus 1, 1, 0, 0. So what is the determinant of this? It is going to be equal to, so this is 0, this is 0, so 1 times minus 1.
Minus 1.
So determinant is obviously non-zero, meaning, so rather than just stopping here, we should be able to appreciate that yes, because the determinant formed from L, V and M is non-zero, L, V and M can form the basis with the help of which I can represent pressure and viscosity. So I should be able to represent pressure, rather the dimension of pressure. The dimension of pressure meaning this particular column vector as a linear combination of L, V and M. Okay. So it means L to the power A, V to the power B, M to the power C. I should be able to represent pressure as this. Do you agree or not?
Yes.
Yes, sir.
So the fact is, here the column vectors are a linear combination of these sums, right? So column vector 1, minus 1, minus 2 is like a linear combination of A times 0, 1, 0 plus B times 0, 1, minus 1 plus C times 1, 0, 0. But having this expression is tantamount to saying that P is L to the power A multiplied by V to the power B multiplied by M to the power C, because the dimensions will add. Okay, so this statement and this statement are equivalent. Dimensions of P will be equal to dimensions of L to the power A multiplied by V to the power B multiplied by M to the power C, and it is nothing but us finding out the appropriate linear combination terms A, B and C to find out what the dimension 1, minus 2, 2 will be through a combination of L, V and M. So quickly find out the linear combination and tell me.
1 minus 1.
So if that is true, so what was the final answer? So what is A, B and C?
1 minus 3, 3, 2 and 1.
Once again, 1,
Minus 2,
minus 2,
1.
1. So let us write this down. So P equal to L to the power A, V to the power minus 2 and C to the power 1. So what is this? Sorry, this should be M. So m upon, are you sure you told me the correct answer?
It should be minus 3.
Minus 3, 2 and 1.
Oh, come on guys, this is not expected. So what is A, B and C? I ask again.
Minus 3, 2 and 1.
Minus 3, 2.
Yes, sir.
So L to the power minus 3, V to the power 2 and M to the power 1. So it is mv square upon L cube. So what is mv square? What is actually, what is m upon L cube?
Density.
So it is rho v square. So bingo, we have it correct. P and rho v square have the same dimension, and we were able to construct, using ideas of linear algebra, the appropriate dimensionless term. So wait, we are still not done. We are still not done because so far we have represented P in terms of that, but I could have very well done this thing instead. I could have written pi 1. So pi is just a placeholder for a dimensionless term. So pi is just a placeholder for a dimensionless term. So pi 1 equal to some combination of pressure times L to the power A times V to the power B times M to the power C. In this case, let us write down the whole thing. Dimension of pressure is M L to the power minus 1 T to the power minus 2 yeah, multiplied by length to the power A. So what is length to the power A? M to the power 0 L to the power A T to the power 0. What is velocity to the power B? It is M to the power 0 L to the power B T to the power minus B. What is mass raised to C? It is M to the power C L to the power 0 T to the power 0. Let us now collect all the terms. So it is M to the power 1 plus C. What is L to the power going to be? Minus 1 plus A plus B plus 0. And what is T to the power going to be? Minus 2 plus 0 minus B. Okay. So essentially, if pi 1 is supposed to be a dimensionless quantity, each of these exponents has to be what?
0.
Good.
0.
So each exponent has to be 0. And thus 1 plus C equals 0. A plus B minus 1 equals 0. Minus 2 minus B equals 0. And thus we obtain B equals 2, C equals minus 1 and A equals 1 minus B, which is minus 1. So then the pi 1 term is going to be P L to the power minus 1.
Sir, B is minus 2.
Sorry. B is minus 2. My bad. No one is prone to silly mistake. No one is
So
immune
A
to it.
will be plus 3.
B will be minus 2. A will be 1
Plus
minus B, so 3. And C will be minus 2. So let us correct it. L to the power 3, V to the power minus 2 and M to the power minus 1. So P upon M V square upon L cube. Essentially it is P upon rho V square. So good. So now you have understood how to find out a pi term, and we have clearly seen the connection of linear algebra of ranks and this, because essentially what you're trying to do is finding out a linear combination of this in terms of this, right? Are you able to connect this? Connect the dot.
Yes.
Okay. So if you do not choose the appropriate basis vector Okay, that is to say, if you do not choose these three terms having, so if these are not from the rank calculation, if LV and M themselves are not linearly independent, then you will not be able to find this out correctly. In order to find pressure in terms of whatever quantities you want to find, these quantities should necessarily have a submatrix determinant to be 0, otherwise it will not work. Okay, and the entire mechanism of this has the basis in linear algebra and finding out the basis of the vectors. So now, fine, please find out as a small exercise the dimensionless term involving viscosity and all these terms. Take 5 minutes and do it. I want everyone to do it. I'll randomly select someone to do it. Okay, okay, my bad. So it shouldn't take so much time, ideally.
-2, 1, and 1, 2.
So let me choose. Let me choose someone. It's very unfortunate that we have to do the class like this. I always enjoy interacting with people upfront. But you know, what can you do? I think I lost connection for a while over there. Am I still
Yes, sir.
audible?
Yes, sir.
Okay. A lot of people seem to be idle or whatever. I don't know. Okay, let's ask someone. Ritik Sachdev. Ritik Sachdev.
Yes, sir.
So can you help us do this?
Yes, sir. A is equal to -2, B1, C1.
Very wow, very good. So let us. I mean, don't just tell me the answer. Let us do the entire working. So pi 2 will be equal to viscosity multiplied by
Viscosity,
L to the power A, V to the power B, M to the power C.
yes, sir.
Then what will I write? I will write viscosity as M to the power,
M
sorry, not 0, M,
1, L minus 1,
hmm,
T minus 1.
so if you just do this calculation, so finally what do you get?
Minus 2,
Minus 2,
1, 1,
1, 1.
1, 1.
So therefore the second dimensionless term will be mu. Are you sitting in a vehicle?
No, sir.
Someone else is sitting in a vehicle. But anyway, so this is the dimensionless term that we have. So the first step that you will always do is find out all the parameters relevant in the problem. Second step, what do you do? So after you find out all the relevant parameters of the problem, what should you do? What have we done?
So in the previous step, I think he mentioned the minus 2, 1, and 1.
Hmm.
I think it's supposed to be for the dimensions of viscosity, and not the dimensionless. I think.
Okay.
You said B should be
Yes, sir.
minus.
The sign should be opposite.
Okay, the signs will flip.
Yes, sir.
So okay, he would have then found out this as some constant multiplied by whatever and then divided everything. Okay, anyway. So let me just write down the rules and just make sure you follow those rules. So the first step is to find out all the relevant parameters of the problem. Okay. Second step is to what? Who can tell me what we did? After finding out all the relevant parameters of the problem, what did we do?
So we find out the basis actually.
Exactly. So we wanted to find out the basis vectors. So when I say we wanted to find out the basis vectors, what I really mean is which combination of terms will I use to make all the other terms dimensionless? Okay. Is this phrasing clear to you?
Yes, sir.
So the way to find out the basis vector is create the entire large dimension matrix. Okay. The thing is to find the dimension matrix and to find out the rank of the dimension matrix. So once you found out the rank of the dimension matrix, you would have answered this particular question. After that, what should we do? So if the total number of terms is equal to n and the rank of the matrix is R, how many dimensionless terms can we write?
N minus 1.
N minus.
Exactly. So once you've determined that you have n minus r number of terms, the fifth step is to find out all the terms, and as a customary notation they are called as pi 1, pi 2, pi n minus r. So they are called as pi terms because the guy who sort of devised this thing, he, his name was Buckingham. And the name of the principle is called as Buckingham pi theorem. Okay, so whatever we have discussed so far is called as the Buckingham pi theorem. Excuse me, I have a phone call. Okay. Okay, so this is called as the Buckingham pi theorem. So we have to find out all the terms, and the sixth step will be to say that okay, the physics of the problem depends some way on pi 1, pi 2, pi n minus r. So there must be some relationship between pi 1, pi 2, pi n minus r, and that can be written as this. So this is like an implicit relationship between the pi terms. You can always convert the implicit relationship into explicit relationship, but for now it is not necessary for us to. But so these are the steps. We will do some more examples. We will revisit the simple pendulum example also, and we'll do some more simple examples. But those of you who are slightly interested in experiments, okay, experiments and all, so for them this is a very, I cannot stress upon how many varies I can put. It's a very useful thing to know which pi terms are there in the problem. So suppose I start doing the experiment with, for the simple pendulum, let us go back to the simple pendulum. Suppose I start doing the experiment without doing this preliminary analysis of dimensions. Now because I have not done the preliminary analysis of dimensions, I will think that mass is an important parameter, so let me keep on changing, let me keep on experimenting with different masses, right? So in the end I'll end up with a bunch of readings for different masses, and it is only after doing a huge lot of experiments that I will conclude that the mass has no bearing on the time of oscillation of the problem. Do you agree with me?
Yes.
So even before doing all this, from an experimental viewpoint, before performing the experiments, with the help of dimensional analysis, I now know which particular parameters I should look at, what experimental combination of terms I should look at. Meaning, if I have a bunch of data from experiments, so I have time of oscillation data, length data, and gravity is always fixed. So if I plot t as a function of square root of L upon G, what will I get? What kind of curve should I get?
A straight line is slope to
No, it will be a constant curve, and the value of the constant will be 2 pi. Okay. But if I don't know that such kind of a combination of term I will expect, I will maybe plot something like this. I will plot t and length. Okay. So then it will be like a square root relationship. I will find this curve, right? So forming this kind of dimensional analysis gives us more insight into experiments. It helps us do lesser number of experiments. How does it help in doing lesser number of experiments? Well, let's see through see through some examples. So let's make a new page. Okay. Let us revisit the problem of the simple harmonic oscillator, and let us do it through the Buckingham pi principle. So the first step, this is the physical problem: mass, length, gravity, time of oscillation. So let us write down time, mass, length, gravity. Let us write down the dimensional matrix. So we have already identified the parameters, and let us find out the dimensional matrix. So what is the dimension of time?
001.
0, 0, 1. Mass 1, 0, 0. Length 0, 1, 0. Then,
Zero.
and gravity
01 minus
0, 1, minus 2. Now let us find out the rank of this dimensional matrix. So what is the rank?
The 3.
2. Yes, sir.
So the rank is equal to
3.
3. So you chose which terms to find the rank?
TML.
TML.
Okay, don't take TML because, okay, we can take TML, it doesn't make a difference. We can redo the calculation with TML. Let us take M, L, and G in this particular case.
Okay.
Because ideally we want to find out an explicit expression for T. So try to keep T separate. Okay. So then let us try to, so the number of terms are 4 and the rank is 3. So the number of pi terms will be only 1. So 4 minus 3, only 1 term. So that pi term will be T m to the power A, L to the power B, G to the power C. And this is essentially going to be m to the power 0, L to the power 0, T to the power 1 multiplied by m to the power 1, L to the power 0, T to the power 0 raised to A. Okay, so let me directly write down L to the power B to the power 0, and G will be m to the power 0, L to the power C, T to the power minus 2C. And thus we have pi 1 equal to the power 0 plus A, L to the power 0 plus B minus C, T to the power 1 minus 2C. So C will become equal to half. I mean, let me not skip the step. 0 equal to 0 plus A, 0 equal to B minus C, 0 equal to 1 minus 2C. And the reason I can write this because I know that each of the exponents has to be equal to 0. Thus A equal to 0, B equal to C, and C equal to half. So therefore
Is equal to minus.
B plus C, it is B plus C. Okay.
So B plus.
Okay. Actually, I was just testing your awareness. So then B becomes equal to minus half. So then what is the pi term? It is going to be T m to the power 0, L to the power minus 1 minus half, G to the power half. Essentially T times square root of G by L. And because there is only one pi term, it is going to be equal to a constant. Okay. Is this okay?
Yes.
Yes, sir.
So now let us proceed to a slightly more fluid mechanics experiment, and from that we will see how a great engineer was able to make a very comprehensive chart. Give me 2 minutes. So I'm surprised everyone has a good stable internet connection. So far at least. So let us consider the scenario in which we have pressure drop in a pipe flow. Let us draw the schematic of this. So obviously in a pipe flow we have to draw the pipe, right? So across the pipe we have a certain loss in pressure. So the parameter list, let us write it over here. Delta P is the pressure loss. Okay, what are the other parameters you can think of? The length of the pipe.
Coefficient of viscosity, area.
The length of the pipe.
Length of pipe, coefficient of viscosity,
Okay, one
area,
more. One by one.
Velocity of flow.
and velocity.
Velocity of flow. The diameter of the pipe. The reason I'm not writing the area again, because writing the diameter is tantamount to writing the area also. Is it not?
Of course.
Because diameter, area, they are not independent dimensions. And diameter literally, pi d square by 4 is going to be the area. So coefficient of viscosity, good. What else?
Pressure maybe.
Pressure is
Okay,
already
the
here.
process, that is it. Yeah.
The density of the fluid.
The temperature then also.
No, not temperature. There are no thermal effects as such. And right now you may think that this is the entire list, but there is one little roughness of the pipe. So one more physical parameter is the pipe roughness. So don't worry, you will be given all this. You will be told that these are the useful sort of parameters of the problem, and the thing that we want to find out is the delta P. So let us form the dimension matrix. Let us write all the terms down. So pressure, what is the dimension of pressure?
1 minus 1 minus 2.
1 minus 1 minus 2. Length 0,
0,
1,
1, 0.
0. Dia
0 and 0.
epsilon.
Maybe all 0.
No, roughness is also having a RMS length.
Oh, okay. I thought it might be dimension.
No. Eventually it will become dimensionless. Eventually it will also become dimensionless. So U, velocity,
0, 1 minus 1
density,
minus 3. 1 minus 3.
viscosity,
1 minus 1 minus 3.
okay.
So why did you assume the roughness to be of the dimension of length?
I did not assume the roughness to be of the dimension of length. Roughness has a dimension of length. In your first year, I think that experiment is there in third year. Third year mechanical engineering students have to measure the roughness of a surface. The roughness is usually measured as a micron. Okay, roughness is a unit of length. It is not a dimensionless quantity. So now this is the parameter we want to eventually find out. So let's not play around with this in the rank. L, D and epsilon, all of them have the same dimension. So look, so tell me what the rank of this will be. What the rank of this fellow will be.
Zero.
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 No, it will not be 0.
1.
It will be 1. It will be 1. Meaning out of these 3 terms, you can choose only one basis vector.
Right.
And obviously all of them have units length. So obviously we can choose only one of them. So obviously we will not use this. So let us keep the length to be one of the parameters. What about u and rho? Someone lives near a railway track. I can tell for sure. So tell me, if I choose this submatrix, I can very well choose this submatrix. So L, U and rho submatrix. 0, 1, 0, 0, 1, minus 1, 1, minus 3, 0. So what is the determinant of this?
Minus
So determinant of this is minus 1.
minus 1.
Meaning I can choose L, U and rho as my basis vectors to represent delta P, D, epsilon and mu. The total number of terms are 7, while the rank is equal to 3. So dimensionless terms will be 7 minus 3 equals to 4. So before even doing that, I mean, you are very good in eyeballing things. So tell me 2 pi terms already. You can directly, by seeing this entire thing, you can tell me 2 dimensionless terms already.
Delta V and coefficient of
No. So I am asking you to tell me 2 dimensionless terms out of delta P, D, epsilon and mu. I am telling you to name 2 dimensionless terms directly.
D by L and epsilon.
Excellent. So it will be D by L and epsilon by L. That's a no-brainer. That's an absolute no-brainer, right? Do you agree with me?
Yes.
You don't even need to do all those A, B, C, coefficient, blah, blah, blah. It's sitting right in front of you. So now the only thing that remains to be done is delta P multiplied by L to the power A multiplied by U to the power B multiplied by rho to the power C and viscosity multiplied by L to the power A U to the power B rho to the power C. Remember, the ABC for this is only for this. The ABC for this is only for this. ABC is just to find out the coefficients. These are not equal. Huh? Across different terms, they are not supposed to be equal. I hope that was clear the very first time we introduced it. Let me save this file. Okay. So what will it be? What will pi 3 be equal to and what will be pi 4 equal to? No, tell me the direct, all the entire terms. So it will be something like this.
Yes, sir.
And actually, from experience only, I can tell all this because I've been doing it for a while now. So the different pi terms are d by L, epsilon by L, delta p by rho u square, mu upon rho u L. Okay, so this is like the pipe aspect ratio. And actually, epsilon by L sort of has no physical meaning. Okay, but it is actually, it can be written as epsilon by d multiplied by d by L. Epsilon by d is like the relative roughness. Delta p by rho u square is like the dimensionless pressure. And mu upon rho u L can actually be written as mu upon rho u d multiplied by d by L. And mu upon rho u d is like the 1 upon Reynolds number. We will come into the definition of Reynolds number and all this later. So pi 4 is like 1 upon Reynolds number times the aspect ratio. Pi 2 is like the relative roughness multiplied by the aspect ratio. So this is effectively relative roughness multiplied by the aspect ratio. I mean, to avoid all this aspect ratio business coming in, you could have very well chosen the, instead of L, you could have chosen the basis term to be D, the diameter. But anyway, now that we found out, we can now say that there exists some relationship between D by L, epsilon by L, delta P upon rho u square, and mu upon rho u L. There must exist some relationship between pi 1, pi 2, pi 3, pi 4. Let me now paste something over here. Uh, are you able to see the screen or not?
Yes, sir.
Yes, sir.
I mean,
Yes, sir.
which screen in particular?
The pi is equal to those both
Okay, okay.
pi.
The same screen, right?
Yes.
So this particular diagram is called as the Moody diagram. Okay, it is called as the Moody diagram, and if you look at the various terms in the diagram, on the axis, the y-axis, you have something called as the friction factor. Definition of friction factor is 2d delta p upon rho v square L. Essentially, it is what, in terms of our pi terms, what is plotted on the y-axis? It is nothing but pi 3 multiplied by pi 1. Do you agree? I mean, I think you really have to squint hard to see this particular expression.
So what is the physical meaning of friction factor?
It will come much later. I mean, the physical reason, meaning of friction factor will be discussed much later in the course when we study viscous flows. But essentially, it is sort of the pressure loss represented in terms of a head, which is rho u square. So pressure loss due to velocity, sort of. Okay. So the point right now that I'm trying to make is on the y-axis you have pi 1 multiplied by pi 3. Do you see this or not? See, forget this 2 factor. Forget about this 2 factor.
Yes, sir. Yeah.
So it is d upon L, and the other term is delta p. Give me a moment. I have a phone call. Yeah, hello. Okay, so on the other y-axis, you have something as epsilon upon d. So what is epsilon upon d in terms of our pi terms? What is epsilon upon d in terms of our pi terms?
Pi 2 by pi.
So it is nothing but pi 2 upon pi 1. So on the x-axis, we have this. On the x-axis, we have rho v d by mu. So what is that particular term in terms of our pi terms?
I 4 by 5.
Pi 4 by pi 1.
No, it has to be
Pi 1 by pi
Pi
1.
1 to pi 4.
Pi 1 by pi
it has to be pi 1 by pi 4. So with the help of this plot, this entire plot encompasses the different pi terms, pi 1, pi 3, pi 2 and pi 4, and it incorporates all the data from various experiments. So you can do whatever experiment you want, just have to find out what pi 1, pi 3, pi 2 and pi 4 are, and then you can sort of land up on these curves, one of these curves. So with the help of dimensional analysis, so suppose you were not aware of dimensional analysis, suppose dimensional analysis was not there. So each time you change another pipe, another diameter, you have to redo the experiment to find out the pressure loss. Each time you have a different pipe roughness, you have to redo the entire experiment to find a different pressure loss. Each time you have a different flow velocity coming in, you have to do another experiment to account for that velocity. Each time you do an experiment with a fluid of different viscosity, you have to do the entire experiment again and find out the pressure loss. But no, we know through dimensional analysis that okay, it does not only depend on density or viscosity. It depends on the combination of terms. It depends on the various combination of terms. So I can take a 1 meter pipe with a roughness of 1 millimeter, or I can take a 1 centimeter pipe and a roughness of 10 micrometer, and both will have the same physical manifestation in finding out the pressure loss. So I hope I am able to impress upon you how useful this kind of things are. Okay, and in the assignment, so today I will give one assignment, and I will give you a very long deadline, like until next Wednesday or something, and you will see that those problems, some of those problems will not even be from uh, fluid mechanics. There will be something from optics. See, any, so you know, you can do one thing, you can go back to your class 11-12 physics books. You can open up Resnick, Halliday, H.C. Verma, whoever floats your boat. You can look into their solutions, some of the closed form solutions, analytical solutions, and you can see that whether you can apply dimensional analysis to find out some sort of physical resemblance of the closed form solution from just preliminary analysis of the physical problem. Okay, and
So what
bonus,
does solution?
closed form solutions meaning like we have the solution for the simple pendulum t equal to 2 pi square root of L upon g. So as opposed to a closed form solution, you have a solution where you have governing equations, but everything else you find out numerically. That is not a closed form solution.
All right.
Okay, so basically an algebraic solution. So go back and see if you can identify some of those terms. I could identify many terms in electromagnetism. Take a look at Biot-Savart law or Oersted law, so things like that. You will see that you can do a lot of things. Of course, Biot-Savart law will, you have to introduce new dimensions of magnetic field, ampere, and all these things. Okay, just think about some of the things you have studied in optics and all these things. You will see, okay, things actually work out, and in many cases you could assess what the dimensionless nature. Okay, so dimensional analysis could no way tell me what the functional relationship between this will. I cannot tell whether delta p upon rho u square will be equal to mu upon rho ul raised to the power of a times epsilon upon l raised to the power of b. No, it cannot tell me this functional form. This functional form has to come from either experiments or some more numerics or theoretical considerations. But imagine this, without even solving anything, you could determine what the useful groups of terms are going to be, which will aid you in designing your own experiments, or will aid you in designing the theory. Here in this table you can see some simple roughnesses that are given. Roughness for concrete pipes 0.25 mm, for smooth concrete it's 0.025 mm, and so on. So engineers have gone and done that calibration calculation. They have put in a lot of effort to do all this. Okay, so anyway, I think let's wrap up this particular lecture. Let me stop recording.